let us now explain the mechanism of finding the correct set of weights to solve a prediction problem. So, we have seen in the last lecture is that we can realize certain logic gates, for example, and OR by proper choice of the weights W. So, this is interesting because what we can do is that the same neuron we can assign different weight values to realize different functions. Functions means some target mapping. Say if this is, say for example, AND, if this is the input is 1 1, output should be 1. If input is 1 0, output should be 0 or minus 1. So, like this, given any input output function, input to output mapping, the same neuron can realize it for by changing just the value of the weights and the bias. So, this the same neuron, these are called the architecture of the neural network, the structure of the neural network. And what we are trying to say is that the same architecture, same structure can be used to learn different input output mappings for by varying the value of the weights. So, in the next part what we will see is that, so now given some input output mapping, given some training examples of input output mapping, what is the proper value of the weights that will achieve this input output mapping as close as possible. So, as you know, so what will be given is that will be given some training examples T, which will be some xi y, a number of xi yi, like previous problem. So, this yi may be either class level 0 1 or minus 1 1, or it may be some real value. We are given a number of such weights. You have to find a set of w's which given a new x will correctly or as close as possible to correctly predict y. So, the general technique of this training is as follows. You start with initialize w to some random values, initialize the initial weights w1, w2, w0 to random values and then update the weight. So, the rule is values update w's as we see the training example xi yi is. 3 till w values do not change significantly. So, this update will go on, we will call this iterations of update. Over 2 successive iterations, if the w values do not change significantly, we stop there, okay, and use that w for predicting for a future point. We will consider 2 such update rules. We will consider 2 update rules. The update rule will be of the following form. So, we have some initial value of w and this we are updating. Say suppose at certain time in a certain iteration we have a value of w equal to w, let me call it w old, current value of w. we will see an example and rectify this value of w by adding an update term delta w. Okay. And this new value will be our new value of the weight, updated value of the weight, and this will continue. So, next w new will become w old, again we will do w w and delta w and we compute w new, go on doing this when the difference between w new and w old becomes very small. So, we will study two rules as I have said, the perceptron rule and the delta rule. Geometrically, a way of viewing this is like this. So, back to the same picture, if you have positive and negative set of weights, you start with a random perceptron, random w. Random w means random line, separating line. Now, you delta it so that it gets rotated and shifted till it becomes a good discriminator for all the training points. Okay. Actually, this can also be looked upon as an optimization problem. So, if you look at all your w values, w1, w2, other values of w2, other values also, and we define as a error that given certain value of w1, w2, w0, how much error we are making in predicting y. So, if you plot that value of error along the z axis for different values of w1, w2, w0, you will get something called a error surface. What we want is that find the optimal value of w, the value of the weights which gives you the least error. Okay. So, that way it is a minimization problem also. Okay. So, we will see this. The first algorithm is kind of easily visualized by you have a arbitrary plane sign line and you gradually tilt it by correcting your w. W we will call w vector as the vector of the pair w1, w2, w0 till it becomes separable. Now, I will write down the algorithm. Okay. So, as I have mentioned, this is the update rule. Take any wi is for any w. I have apply your threshold function, you get your y. So, take any w, its new value is the old value. You start with a random initialization, old value plus some delta w as I had mentioned. Where what is delta w? Delta w is your target minus output. So, what is target? Say some for some value of input, say 1 1. Suppose you are learning the end function. So, if input is 1 1, output should be 1. If your input is, say this is the end function, your input is 1 1, output should be 1. If your input is 1 1, let us say this point 1 1, output should be positive. So, this desired value is what we call as a target value, is the desired value. Given x, what is the output you want? But maybe the current value of these w's do not give you the desired value, but it gives some value. If you take x1 into w1, x2 into w2, the plus w0, put the threshold, some value of y it will get. That I call as O, the output value. What we do? You take the difference between target and output, actual output and target. multiply by that by the x, the input vector. Note these are all vector terms, delta w is a vector because w is a vector, x is a vector, x1, x2. And your eta is a learning constant, learning rate, usually small, say 0.1. Okay. So, you multiply that and this as your update rule. So, this is my update rule. So, you note one thing, that if your target output and actual output matches, then delta is 0, no change in weight. Only when it does not match, then you have a change in weight. So, this is an example. There is actually another way of looking at it. Suppose I have two inputs, it will be W1, W2 and the W0 bias, that will be the weight vector. Input vector, it will be x1, x2 and third input x0 is always 1. So, I write it as 1, bias input. And you have a set of training samples. Okay. So, this is a vector, this is either +1 or -1 or something, +1, 0 also you can write. So, the rule is as follows. Look at a training instance x I y I. If the output value for x I is same as y I, do not do anything. In other words, if a particular x I is correctly classified by your W, do not do anything for that x I. Otherwise, if it is misclassified, if it is in the misclassified by this, that is class level and predicted O does not match, otherwise update W. How you update? Plus eta times, note if it does not match, t minus O is 1, otherwise it is 0. So, I am not writing t minus O, I will that will be 1 and x I. So, what you do, your new vector W vector is the old W vector plus your eta times x I times x I. Okay. often in perceptron rounding rule, this eta, particularly in the rule, eta is taken to be 1, and you get this nu w. So, you can see what is meaning that this is your w vector, this is your x. If it is misclassified, you tilt it more towards that, so that you include it in the positive side, tilt it, make it nu w nu. Okay. So, this is just another form of writing the perceptron rule. Minsky and Peppert, two scientists, famous artificial intelligence people, Marvin Minsky of MIT, he showed long back that this update rule is always going to converge if the classes are separable. That means, if you have classes like this that are separable, whatever random w start with, if you follow this rule, after some time it will get a proper value. So, of course, I am not talking about sigmoid, I am talking about only threshold function, activation function. By a line. This was a nice result. All right. So, coming back to our discussion, now let us look at, so this is clear, I guess. So, let us look at the second rule, second weight update rule, which is the delta rule. This rule uses the following philosophy, a philosophy known as the gradient descent. What is the philosophy? So, as I had said, it considers something called a weight space. What is weight space? You take all the weights as axes. Yeah, I can draw more. Okay. So, a given set of weight values is a point in this weight set, weight space. Weight space. Okay. This is one. So, you can have different type of weight values. There may be more weights, I am not drawing them because you cannot visualize. And in the z axis, you plot the error. What is error? See, if you take certain value of weight for some input, you will get some output. Some set of inputs will get that output, let me call it as OI, may be same as target value TI, but the desired output, or may not be same. So, the error is this difference. Okay. So, one possible way of computing error is what is called a mean squared error. Is half summation all the training points square. So, if you fix your value of w, you get some error. Now, if you change your value of W, you get a different values of error. If you plot them, you get the error surface. And weight learning is nothing but finding a weight which gives the minimum error. Now, let me tell you a technique of doing that. Suppose I have a function f x, it looks like this, let us say. All x, this is what you have to find. How do I do? Guess, take certain value of x, x naught, let me call it. Draw a tangent to f x, see where it intersects, that we call as x 1. Look at f x, again draw a tangent, call that as x 2. You see, if you go on doing this, soon your x I will come to the minima. For functions which are well behaved, look parabolic. If the function is like this, it will not work, or if the function is like this, again it will not work, it may stop here. Okay. Fortunately, the perceptron error looks like this. Okay. So, you can calculate the gradient and do like this. So, this is the fundamental principle of something called gradient descent. So, we have a rule, the delta rule, which is based on this technique. I will explain it. So, this is what I have said. Okay, it is. So, another way of looking at it is like this. Suppose you are in a mountain, you have to come down. What you do? You look around, find out which direction the slope is steepest, take a step, again look around, take a step. If you do this, you will eventually come to the lowest point. You will eventually come to the lowest point. That is the fundamental principle. So, this method is used for deriving the delta rule, not going through all the derivation, but you can finally write down your training algorithm as this. Sorry. After computing all this delta and everything, you can comment like this. Initialize to 0, let us say random value, and this is your update rule, same as before, okay, and update weight. So, this is known as the delta rule or the LMS rule. This is guaranteed to converge to the correct value. I am not going to the derivation that this is indeed. So, as I have said, the rule is take the steepest descent, look around which direction, which change in delta value or W value, delta W will give you least maximum reduction in error, change it in that direction, go on doing it till you converge. Okay. So, this is the gradient, almost same functional form as the Perceptron rule, except for that you add up over your error function is sum up over all the training set, otherwise earlier in the Perceptron rule it is the not sum, but single input error. So, this is the gradient rule. In the next lecture we will move on to more complex functions than a linear hyperplane. Thank you.